Thank you very much for inviting me. It is too bad that I cannot visit Mainz in person. I guess so. The next best thing is to be here virtually. I'm Jeanie Lau from the Ohio State University in Ohio, in the U.S. So today I'm going to tell you about. So this is flat bands in flatlands. So this is a rather generic title. So in particular, I tell you about our works on topological and correlated phases in Bilayer graphene. Okay, so our physicists here, we probably don't need this introduction. Just want to say we love interactions. May or may not be the human kind, but definitely the electronic kind. So the interaction gave us all the interesting phenomena in materials, and that's including superconductivity and magnetism. That is the topic of this workshop. So flat band, one simple parameter to parameterize the interaction effect of how flat the band is this fine structure constant, or sometimes we call interaction parameter, which is basically the ratio of between Coulomb energy and Fermi energy. And so it goes like this. So so it goes inversely proportional to the dielectric constant of the environment, and it also depends on the gamma, which is the power of the energy momentum dispersion. So if you have a larger gamma and the band is flatter, right? So it's then you have a larger you have a larger interaction strength, and then usually this is the interaction strength goes lower at smaller density. So in most cases, we want to get to as low density as we can. Okay, so these are the flat band. So how do we generate flat band? So I think fairly generally we have like, for example, 3 ways to generate flat band. So I'm going to tell you about some examples from each of these categories. So the first technique is, of course, just to use the magnetic field. Of course, for example, in graphene, we know that the band structure have this massless direct fermion dispersion, and so it's really not flat at all. It's very pointy. But of course, we can generate flat band. So just say that interaction parameter is actually, we just work through the algebra, is about 2. So it's not that strongly interactive. And the worst thing is that this is a constant because of the linear dispersion relation. This interaction parameter is a constant and does not depend on charge density. So we cannot get to higher interactions by going to lower density. And so monolayer graphene is only weakly interacting. But of course, we can generate a flat band in any system by using the magnetic field. In this case, we have the formation of Landau levels, which is, of course, completely flat. The kinetic energy is completely quenched. We have extremely large density of states. And so and this, of course, gives us a quantum Hall effect. And so in the quantum Hall effect, it will be then we have things, for example, like quantum Hall ferromagnetism. And so one example is saying monolayer graphene, right at the charge neutrality. So this is a quantum Hall state at filling factor 0, and this, of course, this state is actually has no counterpart in traditional semiconductors because at filling factor 0 at the charge neutrality, traditional semiconductors has a gap. So this state is rather unique to graphene and few layer graphene systems. So in this monolayer graphene, it's insulating with a diverging longitudinal resistance. And so this was the first reported by Owens Group in 2008, and then followed, and then there was a lot of work from quite a few works from other groups in the field. this experimentally, it's shown to be, this is by work from Andrew Young in Pablo Herrero's group back in 2014, that this state, this insulating state, is an EC plane antiferromagnetic insulator, in which spins in the two different sublattices oppositely polarized in the XY direction. I should say the theoretical prediction for this state is actually predates this experimental work and was provided by Karatanov in 2012. Okay, so now this is basically a antiferromagnetic state coming from the electronic interactions in graphene. So what can we do with that? So this is the one proposed theoretical proposal by Taike et al. Back in 2016. So we can use this to realize spin transport in an antiferromagnetic insulator. So the idea is to use this antiferromagnetic insulator state in graphene to, basically this will be the medium to transport spin. And then we are going to inject and detect spin using the spin polarized edge state at filling factor 0. And so this is really nice proposal, because then we can sidestep the a lot of problems associated with conventional antiferromagnetic insulators, for example, the uncontrolled interfaces or undesired anisotropy. And so in this case, we have, because our interface it's an old graphene electronic circuit, so the interface will be perfect. Basically, we are just changing different regions of the of this entire sheet of graphene into antiferromagnetic state in the center, and the spin polarized edge state on the side. Okay, so this is some of our data. So the device geometry is like this. So we have a center region that we're going tuned into the filling factor 0 state. So the numbers in the here shown on the device shows the filling factors of the device. So basically, we have a lot of gates on the device, and we're using the gates to tune different regions of the device into different filling factor states. So the center is the filling factor 0, and then we have this gray region turning to filling factor -2, which is the metallic state and has no spin polarization. And now we have this one yellow area on the left and one yellow area on the right. The yellow area on the left is the injector region, and we're now here we can use gates to make this filling factor of this region tunable. And same on the detector region. And so now we apply a bias between the two filling factor 2 states on the left, this to establish a chemical potential difference between spin up and spin down states. And then so the if this injector region is turning to filling factor -1, this will act as filter, so that only filling, for example, only spin up spin electrons will go through. And on the detector side, we have the reciprocal setup for the detection, and we'll measure the non-local voltage between the filling factor 2 states. And so here we have basically our result. We're plotting the non-local voltage measured here as a function of filling factor of the injector and the detector region. And so here we see a very strong non-local voltage only when both of the injector and the detector region are tuned into filling factor 1, which is a spin polarized state with a spin polarized edge state. And so, and then we also have a control experiment, I guess it's not shown here, where if we turn the center region into filling factor to -2, we also do not see any signal, non-local signal. And so this tells us that we actually do have we're seeing basically non-local signal only when the center region becomes an antiferromagnetic insulator, and the detector and the injector region has spin polarized edge states. Okay, so in this case we have demonstrated long distance spin transport through antiferromagnetic insulator. So I just should mention that this width of this center antiferromagnetic insulator region is about 5 microns, and so that's actually quite so a few thousand times longer than the prior works. And well, of course, the evidence is not complete, but we have reason to believe that this is the spin transport is by a collective spin movement, so-called spin superfluidity in this case. So we can use graphene to function as a clean tunable model system to study ferromagnetic and antiferromagnetic spintronics. So this is a really new field, and we have many open questions. So for example, we have all the length dependence, width dependence, and in particular temperature dependence, and the length dependence will be very important to establish the mechanism of the spin transport in this case. And other questions such as the spin edge, the edge state equilibration, a spin damping mechanism. Can we use bilayer graphene, for example, to now we can use out-of-plane electric field to control the spin direction, and perhaps we can even start to think about more fancy devices such as spin-Josephson junctions, etc. Okay, so all right, so this is a work on the monolayer graphene, but how about other field layer graphenes? So so here we actually I want to show you that turns out this filling factor 0 state, so I write a charge neutrality in the field layer graphene has a very rich phase diagram. So for example, this in bilayer graphene, this is work from Philip Kim's group, where they show that this is in the quantum Hall regime, the bilayer graphene is an antiferromagnetic insulator. And then, if you do not apply, if just a pristine bilayer graphene, very clean, you start out with an antiferromagnetic insulator, you apply an out-of-plane electric field that will push the electrons to reside in one of the outer layers, so this becomes a layer polarized insulator. And at the if you apply a large in-plane magnetic field, they will become eventually a ferromagnet. This ferromagnet is actually a topological state with counter-propagating edge states. So, okay, so what about, we'll go to thicker graphene, what happens? It turns out the phase diagram actually becomes richer. So this is our recent work in A stacked, so-called now stacked tri-layer graphene, where we can identify actually 4 different phases. So for example, the phase 1, which is right here, it has a complex conductance of roughly 4 conductance quantum. And phase 2 have two conductance quantum, and phase 3 is phase 3 and 4 are insulators, but the transition between them actually goes through, so it's non-monotonic, goes through a local maximum. So it's we have identified that so basically phase 1 and 2 we call the quantum parity Hall effect, quantum parity Hall ferromagnet, with parity, which basically it denotes whether the monolayer and the bilayer bands of the device of tri-layer graphene, which have different, so even and odd basic parity with respect to the mirror reflection symmetry. And so in this case, we have basically a symmetry protected topological phases, phase 1 and 2, and phase 1 has 2 counterpropagating edge states, 2 pairs of counterpropagating edge states, and phase 2 has 1 pair of counterpropagating edge states. And phase 4 is a layer polarized insulator, and phase 3 is what we call a quantum valley Hall ferromagnet. So in tetralayer graphene, now okay, the phase diagram is different. So you can see every time we even go to thicker graphene, we got some interesting result. So here we start out with an insulator, which is phase 1, and then we have this kind of non-monotonic dependence on this is outer plane electric field and magnetic field. And then we have phase 2 and 3, and phase 1, phase 2, we have turns out phase 2 and 3 are both topological phases. Again, they have a quantized conductance, and phase 2, we have 1 helical edge state, and phase 3, we have 2 helical edge states. Okay, so this is just a kind of very rough, quick overview of what can happen in field layer graphene. Shows at charge neutrality point in field layer graphene, and this is all in the quantum Hall regime. It turns out we have all the symmetries. We have layer, we have spin, and we have valley. So these competing symmetries give rise to this kind of really striking phase diagrams. Actually, so a lot of these phase diagrams have topological phases. Okay, so what can we do with topological phases? Of course, it's not easy, but one particular, for example, theoretical proposal is to create a topological superconductivity by coupling them to an ice-swift superconductor. So this is a theoretical proposal which want to create a Majorana zero mode in monolayer graphene in the topological using by coupling to the superconductor as the electrode. So monolayer graphene will be pretty difficult to realize this mode because to achieve this topological phase in monolayer graphene, you actually need a very large in-plane magnetic field, about 20 Tesla, and then you have to couple that to a superconductor that survives the large in-plane field. So what we think, for example, is that in trilayer graphene, phase 1 and 2 are much nicer candidates for this theoretical proposal. For example, this is because we are. I cut out the I cut out the x-axis here. So, but in this case, the phase 1 happens at about half a Tesla, and phase 2 happens between 1 to about 4 and 5 Tesla. So here, right in here is about 5, maybe 5 Tesla. So it will be much easier to achieve this proposal of Majorana zero mode in graphene using, for example, trilayer graphene, because the magnetic field involved is much smaller. Okay, so this is something we're working towards, and hopefully we'll have something to tell you about later. Okay, so let me go to the second part of the talk, which is how we generate the flat band by stacking. Okay, so we know the monolayer graphene have a linear dispersion and it's very pointy, so it's not flat. How about but we can make it flatter by just go to a thicker devices. But it's not just any thicker devices. So in this case, we're actually interested in rhombohedral stacking, which is also called ABC stacking. So we have, for example, in the bilayer graphene, in this case, then you will have a quadratic dispersion. If you go to a rhombohedral stacked trilayer graphene, you will have a cubic dispersion. If you go to a rhombohedral stacked tetralayer graphene, you actually have a quartic dispersion. So you can see the bands as you stack up the graphene, to stick more and more layers, actually the bands becomes flatter and flatter. And so remember, in this case, this interaction parameter goes as is like this. So with larger dispersion power, the power in the dispersion, this alpha becomes much larger, and we can and will also be density dependent. So we can go to, if we stay at low density, this will give us higher, larger interaction. Okay, so and this is like a very brief summary of what we've done in ABC stack field layer graphene. This is basically accumulation of about 4 or 5 of our works in this area. So just to briefly, what we find is that we can, so if we have ABC stack field layer graphene, they are actually intrinsic insulators, and this gap insulator arises from the large density of state and this flat bands in the field layer graphene. And so this gap size actually is about 2 millivolt in bilayer graphene. We find it's about 40 millivolt in trilayer graphene, and about 80 millielectron volt in tetralayer graphene. And the TC increases from about 5 Kelvin in bilayer to about 40 Kelvin in tetralayer. And so this is just some, for example, plot of a gap in the tetralayer graphene. We see this is differential conductance as a function of bias voltage. We see very large density of peaks, very large peaks in the DI/DV curves, which suggests a very large density of states at the edge, pile up at the edge of the gap. And so this gap can be suppressed by large density if it goes away at large density, and goes away high temperature, and goes away at large electric field. So if we apply electric field of either direction, we actually can symmetrically close the gap and recover a metallic state. So this is in all of these states. So we believe it is a layer antiferromagnet at half filling. That is the top and bottom layer are oppositely spin polarized, and this is all at charge neutrality point. So the oppositely spin polarized, and the middle layer sort of doesn't do much. The middle layer doesn't do much. Okay. Okay. So well, this is just some picture. This is another showing temperature dependence data, which we can extract. We can extract the gap size in agreement with what we obtained from this nonlinear IV measurements. Okay, so this is what we believe is a field layer graphene is rhombohedral stacked phase diagram at the charge neutrality point. So we start out with a layer antiferromagnet, apply a large magnetic field, parallel magnetic field. This will start to cant the spins, and eventually it will become a ferromagnet. We apply a large electric field. This gave us a quantum value, which is actually just a layer polarized insulator. Okay, so now what can we? So far what I tell you is a phase diagram at the charge neutrality point. So nominally at 0 doping. So what if we dope these antiferromagnetic insulators a little bit? So what we find that it's very so surprisingly and also excitingly, we find some hysteresis. Okay, so we start. So here is the conductance as a function of gate voltage. So at right at the charge neutrality point, there's really basically it's a very good insulator, and so now so this is to perform the nonlinear IV measurements. So this is what we obtain. So this is conductance is DI/dV. So and we have very sharp peaks. This is a trilayer, so it's roughly at about 40 millielectron volt. Okay, so now if we just dope the sample, a little bit, not too much, okay. And so, but then, if we stay here, then and we sweep the magnetic field, we actually see pretty pronounced hysteresis in the device. Okay, so it goes like that. Actually, so it's somewhat reminiscent of the hysteresis observed in, this is magnetic monolayer by Charlie Chen's group. This is back in 1992. Yep. Okay, so now we think, well, okay, maybe it's not too crazy to think we have some sort of magnetism in the device. In that, okay, so remember our top and bottom layer obviously is being polarized, so we have a layer and the ferromagnet separated by the middle layers, which are, simple model is more or less inert. Okay, so it's almost like a magnetic multi-layer. Well, okay, not really, but okay, there is some similarity to that. Okay, so just to carry this further, so we measure the magnetoconductance, which is relative change in conductance normalized to the conductance at zero field. Okay, so now so for this, I just magnetoconductance measured at different charge densities. So we can see that they actually change as a function of densities. So it gets smaller as we go to more high when we go to higher density. And the hysteresis actually basically goes hand in hand with the magnetoconductance. When the magnetoconductance becomes smaller, the hysteresis also becomes smaller. We also measure this hysteresis and the magnetoconductance as a function of the temperature. So it decreases as a function of temperature, eventually disappears at about 5 Kelvin. Okay, so okay, well, this is just different. I may probably skip this part. We have some. So here we're basically measuring the hysteresis. So we try to parameterize the hysteresis as a function of temperature, and so shows that the cohesive field roughly goes down with temperature, almost linearly. Okay, so to explain this data, we collaborate with Matteo Calandra at CNAS. So he earlier has a prediction that there will be a half metallic state in ABC stack trilayer graphene when we apply electric field that breaks the inversion symmetry and induces spin splitting. And so this is his calculation. This order parameter would go up, as we decrease the density, and so which is okay. At least as a direct comparison is probably not fair, but at least very qualitatively, it kind of seems to match our data. Okay, so well, I should say this is some of this work is already published. So I just want to say that this work from Après has a package group from Columbia, where they also in the ABCA stack graphene using STM, where they see a many-body gap of about 10 milli-electron volt at charge neutrality, and they think it's possibly a ferromagnet. So just to show that we are not completely out of mind, and so this is something that's sort of consistent with our observation. Okay, so how much time do we have? All right. So lastly, I just want to tell you briefly our work on twisting. Of course, this is the one way to generate flat band, and as everyone knows now, by twisting bilayer materials or bilayer graphene, for example, and this is a rather unique way to generate flat band for 2D materials. So we know that if we put two graphene layers together and rotate one of them, this will give us a Moiré superlattice. And this was first predicted by Alan McDonald's group back in, actually, this is 9 years ago, where they predicted a magic angle of 1.05 degrees with super flat band, with large density of states that's unstable to electronic interactions. And so, of course, we fast forward to 2018. This seminal work from Herrero's group have shown that in twisted bilayer graphene with magic angle 1.1 plus minus 0.1 degrees. So they observe a correlated insulating state, a high filling, and a superconductivity when you dope away from the high filling. Okay, so this, of course, have generated a huge excitement in the area as many groups around the world rush to reproduce the data and to observe similar and new phenomena in these systems. So I just want to say that we joined the party, and this work is done in collaboration with Mark Baccarat's group at OSU and Fan Zhang's group at UT Dallas, they did the band structure calculations. So we use a tear and stack technique to produce a sample. And here is a Landau Fan, what we see of the device. So this is a device. Actually, we can see the main peak at the charge neutrality point, and then we see the secondary Landau Fan coming out at the full filling, plus minus 4 electrons and 4 holes in the superlattice. And so from the distance of the secondary peaks, we can calculate that this device has a twist angle of 0.93 degrees, which is actually relatively small, at least based on Pablo's original data, which gives a smallest angle where they observe the superconductivity and correlated insulating state is 1 degrees. Okay, so, and then what we also see is that if we go to beyond the first band, we can actually see the Landau levels coming from when we have 8 and 12 electrons per unit cell. And so this is also consistent with band structure calculations. So band structure predicts that we do have flat band in this case, in the lower band. And if we go to higher band, we have another, here and here and here and here, which direct like dispersion crossing at the higher band. What we also see is that if we dope the device away from half filling, which means we have about a little bit more than 2.7 electron per unit cell, we see superconductivity, and so resistance drops to 0. In this case, with actually with 2-stage decrease in the resistance. Another thing we find is that, again, if we go beyond the first band, the first mini Bourdon zone, when we have plus minus 5 electrons per unit cell, we actually see a very sharp peaks developing, which is here. This is actually, so it's enhanced by the magnetic field, but you can also see that at 0 field, if we go to low temperature, so at 0.3 Kelvin, they're actually fairly, they're very obvious, but disappears about 5 Kelvin. And so this, if we plot this temperature dependence, we see that they have a gap of about 1 Kelvin, and with Landau, so we do see Landau Fan coming out from this this little feature. So this is a quarter filling of the next band with a degeneracy of about 8. So this is, we do see the flat band. Actually, this is at so this is at the quarter. This is flat band at the quarter filling of the higher band. Okay, so for this part, I just want to say that so it's we see that both superconductivity and correlated insulating states in a device with rather small angle, about 0.93, which is below this classical prediction of magic angle. So it's probably instead of magic angle, we probably have a magic range. Another point I want to get across is that electron interactions, we can produce interesting properties and correlated states even at higher density. So we can go beyond the first band, and probably interesting things can also just can happen. Of course, now we have the whole field of twistronics, and with many, many exciting phenomena predicted and observed in, for example, twisted bilayer TMDs and twisted bilayer magnetic materials. Okay, so all right, so maybe I'm just going to, I think my time is up. Let me just to skip all of this. I think we have a lot of opportunity, a lot of challenges. Very exciting time for the materials community and 2D materials community. So with this, I just want to thank my collaborators and my group members, and I'm happy to take any questions.